Hi, in this video, I'm going to talk about mathematical induction, which is a proof method um, that is particularly useful when you have sequences or series, or you have a certain property that you want to prove for a certain um, a number of times. Um, so typically, we have a certain statement, let's say the fact that A union B intersect C is equal to A union B intersect with A union C, which is one of De Morgan's law for set identities. And we have a strong feeling that even if we have A union B intersect C intersect D, then we can do the same thing. More generally, we can, if we have A union B1 intersect B2, intersect B3, and so on and so forth, intersect Bn, then this set is equal to A union the Bi's pairwise with their intersections. So I mean A union B1, A union B2, intersect, and so on and so forth, intersect A union Bn. So since the intersection operator is associative, I mean we can put the parenthesis around this part of the intersection. We can put it on this side, on that side, whatever we want. We can add the parentheses, and it's commutative at the same time. So, but just because of the associativity, actually, we can put the parentheses here and then deal with this part of the equation as one single set, being the set C, and apply this rule to it. So we will end up with A union B1 intersect with A union B2 intersect B3 intersect Bn minus 1 intersect Bn. So this whole remaining part. And we can apply to this part the same De Morgan's law once again to get out A union B2 and then put the intersect operator outside and then add B3 up until Bn and so on and so forth. So we know that we can use this three dot notation to show our reader that our proof is sound, but usually we proceed in a more rigorous way using mathematical induction. You will see that there is another approach called strong induction, and that will be the subject of the next chapter. So let's dig deeper on induction and argue logically why this really works. So the intuition behind is that imagine you know someone who is already on the step number one of a ladder. So, and you know that this person can go from one rung of the ladder to the next one. So you can imagine that just after a while, and after doing repetitively the same action, this person can go up to whatever rung on the ladder. So um, the idea is that if your property is true for a base case, and so you have a certain property that is true for a certain base case, and you have for every k, for every step, if the property is true for that step k, then necessarily the property is true for the next step also. Then using this property and this fact, we know that we can, using mode exponents, we can go from, since P of B is true, then necessarily P of B plus 1 is true. So because of this implication here, and because of P of B, then we can assume that P of B plus 1 would be necessarily true. Now, since the property is true for B plus 1, and given this rule, necessarily the property must be true for B plus 1 plus 1, I mean B plus 2. and it must be hence necessarily true for b plus 3, and so on and so forth. So given this whole property, this implies logically that for every n actually, such as n greater than or equal to b, the property would be true for n. Okay, so this is the intuition behind induction, and it is stated here beautifully. So typically the basis step is 1, but sometimes for certain cases, the property is only true for n greater than or equal to 4 or greater than or equal to 10, I don't know. So this is what we call the base case. In this slide here, we consider the typical case where the base case is equal to 1. The inductive step is to show that whenever we have P of k, then necessarily P of k plus 1 is true. And we prove it for every positive integer k that is greater than or equal to the base case here, 1. Okay. If we do so, then we will finally prove that for every n, the property holds. So actually, how we combine it once again. So by the first step, we can prove the property for 1. Since by considering that k is equal to 1, necessarily the property holds for k plus 1, which is 2. And then we can apply this again and again for 3, 4, 5, 6, and for every integer that is greater than or equal to 1. And we will end up with the property being true for all positive integers n. Okay, this is the same intuition behind dominoes falling one after the other, because the first one was dropped, and given the fact that if the kth domino falls, then the case k plus 1 domino will necessarily fall. And given this same logic again and again, we know that all the dominoes will fall if they are put in the right way. So this is the logical reason behind the behind why induction really works. So if the property holds for a certain base case, so once again they are telling you here at the end that the basis step begins at a starting point B that is so often 1, but it's not necessarily the case. So if we have P of B, and for every K, P of K implies P of K plus 1, it is sufficient to have K greater than or equal to the base case. Here the base case is 1. Then necessarily the property holds for every n. Okay, good. So let's practice on this. So imagine we have this to prove that the summation of the first n integers is equal to n plus 1 over 2. We discussed this example in the introduction session. You remember when we talked about the number of bowling pins that are necessary to fill in n lines. Okay, so if we have, let's say, 3 lines, then we need 1 bowling pin on the first one, we need 2 bowling pins on the next one, and 3 bowling pins on the last line, and so on and so forth. So for n lines in general, we need 1 plus 2 plus 3 plus up until n bowling pins. And we discussed how Gauss and Laplace tried to figure out the formula for it. So if they wanted to sum up all the integers from 1 to 100, they would sum up 100 to get 101, 2 and 99 to get 101, and 398 to get 101, and so on and so forth, until they reach the mid of this sequence, which is 50 and 51. And they will get n plus 1 over 2, n plus 1, n over 2 times, they will get 50 of these 101. Okay, so this is just the intuition behind it. But then how to prove it? Because students often ask, how did we come with the answer at the first place? So often mathematicians would have their own observations, intuitions about the answer, and they just want to make sure that this is true. One way to do it would have been to consider a case, proof by case, and to check the case where n is odd, the case where n is even, and then to conclude that this is always true. But this example is much easier to prove by induction. So in fact, if we consider the summation of all the integers up to 1, I mean only 1 plus nothing else. So the answer must be 1. We know it. But let's apply it to the rule here. So if n is equal to 1, this formula gives us, or arithmetic expressions, can be evaluated to the following. It's 1 times 1 plus 1 over 2. If we do the math, this gives us actually 1 times 2 over 2, which is finally 1. And the summation of all the numbers up until 1 is equal to 1. So it seems that this property is true for 1. But is it true for any other integer? So to proceed by induction, we assume that this property is true up until k, okay? Any k. And we want to check whether from this can, or whether we can entail actually, or whether this implies that necessarily the summation of all the integers up to the next integer, which is k plus 1, whether it's equal to k plus 1 times k plus 2 over 2. So I just replaced k here in this formula by k plus 1, and this means that k plus 1 is replaced by k plus 1 plus 1, which is k plus 2. So we want to check if this implies this, okay? So we need to calculate this, and we need to check if, based on this fact, we can make it to this format here. Good. So actually, we know that this sum is equal to 1 plus 2 plus k plus 1, okay? But we know that this part of the sum, based on our assumption, is equal to this formula a priori. We are proving this. But if we are using this assumption, if we add k plus 1 to it, we do very basic simple math, and we can conclude that finally the summation from 1 to k plus 1 must be necessarily equal to this formula here. Okay? So now we can use this fact to actually to prove, since this formula works for 1, then finally it would necessarily work for 2. And since it works for 2, it must work also for n equal to 3, and it must work for n equal to 4, and so on and so forth. And this is why we can finally conclude that for every n, this property holds. Okay, and this property is what we have stated here. This is P of n. Okay. Okay, let's get another example to get a better grasp of this. So they are asking us to formulate a conjecture about the formula for the sum of the first n positive odd integers. And actually, in ancient Greek, they work on math and geometry specifically. They were trying to figure out how many dots they need to create grids or squarish grids. With one dot, this is the smallest grid. If they want to go to the next grid, they actually need 3 additional dots. So, and here the total number of vertices in this grid is equal to 4. if they want to go to the next biggest grid, like a tiny um, Sudoku grid, they need 5 additional dots, and this will create a 3 times a 3 grid, which ends up with 9 different vertices. So here we have 4 different vertices, 1 vertex, 4, 9, and if you add 7 here, then you will end up with 16, and so on and so forth. So they noticed that the summation of all the odd integers up to a certain odd number to n minus 1 is equal to n squared. Good. So this is an observation. This is an intuition about this summation. And it came from work on geometry, stuff like that. So, but then how to prove it? So they could use certain magical tricks in mathematics to do it in arithmetic, but it's much easier to do with induction. So how to proceed? We can notice that 1 squared is equal to 1. So it means that our property is true. 1 which is equal 1 plus nothing else. So the summation of the first odd integer. And this is really equal to n squared. 1n is equal to 1. So now let's assume that the property holds for k, and let's check if we can entail p of k plus 1 from it. So assuming this hypothesis means that we are assuming that the summation of all the odd integers up to 2k minus 1 is equal to k squared. Good. So what about the summation of all the odd integers up until the next odd integer, which is 2k plus 1? Okay, so 2k is an even number, and 2k minus 1 is this number here. The next odd integer is 2k plus 1. Okay, good. So what we want to do, we want to check whether this is equal to k plus 1 squared. So is it really true? To prove it, we can use our hypothesis, okay? The hypothesis that we assumed just a minute ago. So in fact, this part of the summation is equal to k squared based on our inductive hypothesis. What if we add to it take 2k plus 1? So actually, by doing a certain simple factorization, we can end up with k plus 1 squared. And this proves that p of k plus 1 follows from p of k. And this is true for every k. We didn't make any assumption on k, a special assumption. So it's really true for any k. And therefore, the sum of the first n positive odd integers is n squared for actually any n. Good. Sometimes it's tricky when you want to prove inequalities. For example, if we want to prove that n is strictly less than 2 to the power n, actually, it's tricky if you don't put what you want to prove. So for the base case, there's no problem. If n is equal to 1, then 1 is strictly less than 2 to the power 1, which is 2. This is so easy to prove. Now, if you want to assume that k is strictly less than 2k for any k, and you want to entail from it that the property is also true for k plus 1, so we must show that p of k plus 1 also holds. So to prove it, just state it. So to check what you want to reach. So what we want to reach is to prove that k plus 1 is strictly less than 2 to the power of k plus 1. If you analyze a little bit here, so what you want to prove is whether k plus 1 is less than, so you are just checking this, okay, less than 2 to the power k times 2 to the power 1, okay, if we want to analyze this. So which is less than 2 times 2 to the power k. So given this, I'm doing a little bit of proof, backward proof. Okay, so I'm analyzing my target and I'm checking what I want to reach. So let's check how we can get to this form given this original hypothesis. So with inequalities, sometimes we start with the, so often actually we start with the hypothesis right away, and then we start adding bits to each side until we reach the final format. So here we have k less than 2 to the power k. If we add 1 to both sides, then this gives us that k plus 1 is strictly less than 2k plus 1. Okay, nevertheless, what we want to reach is this form here. Okay, it's not really the same. But we know that obviously 1 is less than or equal to 2 to the power k. Okay, for k greater than, for any k actually. Okay, if k is positive, it's strictly less than. Furthermore, it's only equal when k is equal to 0. Okay. So it's completely legal to make this step and to say that finally k plus 1 is strictly less than this bigger um, value. And this finally gives us 2 times 2 to the power k, which would lead us to 2 to the power k plus 1. Okay, so we agree that sometimes with inequalities you have to do certain magical tricks, but with a little bit of backward proofs, as we did here, you can focus on your target and how you would play with your inequality until you reach the final format. And finally, we reached k plus 1 strictly less than 2 to the power k plus 1 given this hypothesis. So now, given that this is true for n equal to 1, it must be necessarily true for n equal to 2. And it would be the same for n equal to 3 and 4 and so on and so forth. Okay? And once again, we'll end up with the property being true for every n. One last example about inequalities. An example in which we want to prove that 2 to the power n is strictly less than factorial of n. I'm going to do it slightly quickly. So this property actually happens to be true for n greater than or equal to 4. Actually, the property does not hold for 0, does not hold for 1, 2, or 3. You can check it by hand. And the reason is something like this. So maybe the factorial of n goes slowly at the beginning and then very steep afterwards. But the 2 power n goes a little bit steeper at the beginning, and then after 4, 2 to the power n is often less than factorial of n. So for this reason, this property, the fact that 2 to the power n is less than factorial of n, is true only starting from 4. Okay, so this is a typical example where the base case is not 1. Okay, so sometimes it happens, and this is an example of this. So to prove it for the base case, 2 to the power 4 is equal to 16. Factorial of 4 is equal to 24 because it's equal to 1 times 2 times 3 times 4. So it's equal to 24. It's straightforward. The property is true for the base case. Now let's assume that this is true for k, and let's prove it for k plus 1. What we want to prove for k plus 1 is the fact that 2 to the power k plus 1 is strictly less than the factorial of k plus 1. Okay, so without analyzing the inequality, let's already play with the first part of the inequality given the hypothesis actually. So in fact, 2 to the power k plus 1 is equal to 2 times 2 to the power k, which is strictly less than 2 times factorial of k by the inductive hypothesis. But what we want to have is strictly less than k plus 1 factorial. So without loss of generality at all, we can replace 2 by k plus 1. since k is greater than or equal to 4 in our assumption, in our inductive hypothesis, so we can replace, we can keep the inequality and replace 2 by k plus 1. This term is strictly greater than 2. So this whole term is strictly greater than this whole term, which is strictly greater than the original one. And this is nothing else but k plus 1 factorial, okay? Because k plus 1 factorial is 1 times 2 times 3 up to k times k plus 1. And now we have the property true for k plus 1. Good. In this example, we want to prove a property about divisibility. So we want to make sure that n cubed minus n is divisible by 3 for every positive integer n. The property is true for 1 because 1 cubed minus 1 is equal to 0, and 0 is divisible by 3. Remember that a number n is divisible by a certain number m if the remainder of their division is equal to 0. And actually, the remainder of the division of 0 by 3 is equal to 0. So this is why 1 cubed minus 1 is divisible by 3. Let's assume that the property holds for k, and let's check whether it holds for k plus 1. What we want to prove with this is that k plus 1 cubed minus k plus 1 is divisible by 3. So if we replace k plus 1 cubed by its development polynomial, and we subtract k plus 1, we have to do the rearrangement of the terms in a way to get a useful information from the hypothesis, which is k3 minus k is divisible by 3. So we have this divisible by 3 because of our hypothesis. And if we end up with this term multiplied by 3, then this is also necessarily divisible by 3, no matter what the value of k is. So we end up with two terms, the summation of two terms that are divisible by 3, and the final summation is absolutely necessarily divisible by 3. So, which proves that the property by induction holds for every n. In this example, we want to prove that the number of subsets of a certain set, which is the size of the power set of S, is equal to 2 to the power n, where n is the size of the set or the cardinality of the set. So, and which is denoted in this way. So the size of the power set of S, as any set S, is equal to 2 to the power the size of the set S itself. Good. So actually, for an empty set, this property is true. In fact, the size of the empty set is equal to 0, and 2 to the power 0 is equal to 1. And the power set of the empty set is equal to only one singleton, one element, which is the empty set itself, being put as an element within a set. So the size of the set is equal to 1. Well, the inductive step is to assume that the property is true for a set of size k, and to check whether the power set of the set union one additional element, I mean a set with size k plus 1, is equal to 2 to the power k plus 1. So in fact, this is easy to show with a diagram. Let T be the set with k plus 1 elements. So it means that T is equal to the set S of size k union one additional element A, where A belongs to T and S is equal to T minus A. Okay, so the size of S is equal to K. Okay, and the size of T is equal to K plus 1. So if the property is already true for K, I mean the power set of S is equal to 2 to the power K, where K is equal to the size of S, then necessarily the power set of t is equal to 2 to the power k plus 1. So actually the power set of t is equal to 2 times 2 to the power k, so which is finally 2 to the power k plus 1. But why we have this? So because every subset in or every element in the power set of t, which is a certain set x, so for every subset x of S, there are exactly 2 subsets of t. The subset x itself, I mean without the a, and another subset which is equal to x union a. Okay, so we will go over all the elements in the power set of S. Imagine we have 2 to the power k1 elements, and in each one of them we will either copy the element as it, okay, or we will copy the element and we will add a to it. So we will end up with 2 times 2k elements in the power set of t. Okay, and the size, final size, is equal to 2 to the power k plus 1. Good. So you have noticed how powerful the proof by induction is, and helpful instead of using 3 dots in our proofs, or to prove them in different ways each time. Once we have a property that is being repeated again and again for larger sets, for larger elements, for larger values, then we can actually use induction. However, sometimes proof by induction might be misleading, because we may prove that the property is true for a certain base case, and we may show that if the property is true for k, then the property is necessarily provable for k plus 1, is necessarily true for k plus 1. But this would be misleading if actually for a certain reason, the property, assuming that the property is true for k, it's helpful to prove it for k plus 1, but it is not always true for every k that is greater than or equal to the base case. Okay, so the problem is that we are assuming this for every k, and maybe the nature of the problem or of the property makes it not provable, not true for a certain value, specific value that is greater than b. Maybe it's not true for all the multiples of 5, let's say, or the multiples of 10 for a certain reason. So it might be true for every k except certain cases. And in this case, we cannot say that the property holds for every integer. So if it happens that we prove the property for b, but and we assume it for every k, and we find ourselves able to prove it for k plus 1, maybe this is not sufficient as an argument, because for specific case, the property does not hold. Okay, so we may have the implication holds for every k, and it means just in case you have p of k, then necessarily p of k plus 1, but maybe for specific cases, for specific values, the property does not hold. And this what leads us to strong induction, what we'll see in the next chapter. With the strong induction, we assume that the property is true for b, or actually we check that the property is true for b, we prove it also for b plus 1, and for b plus 2, and so on and so forth, and for k. And given all these facts, okay, we prove that this necessarily implies that the property is true for k plus 1, okay? And in this case, we can be more confident that the property is finally true for any n, okay? So let's check an example of pitfalls in proofs by induction. So the example here is to prove that for every set of n lines in the plane, no two of which are parallel, these lines meet in a common point. Okay, so if we have two lines, that are not parallel, they must meet in a common point. Okay, so we have line 1, line 2, they necessarily meet in a common point if they are not parallel. Okay, what if we have three lines? So, actually, this is not really true. So sometimes it happens that the three lines meet in a certain common point, but sometimes if we have these two lines, maybe the third line is going there, is missing this common point. So and it will have, like they will have three uh, different points that are common to each pair of lines. Okay? So we know that this property is not always true. It's not true for the case of 3. Nevertheless, if we assume that it is true for every k that is greater than or equal to 2, weirdly, we can entail from it that p of k plus 1 is necessarily true. You see the problem here. So once you make this wrong assumption, p of k, nothing prevents you from entailing the wrong conclusion, p of k plus 1. So just because p of k is false, it does not mean that the implication is false. The implication is still true. Okay? So how do we prove it? Um, or how we might prove it erroneously. So if our inductive hypothesis is the following, p of k is true for every positive integer that is greater than or equal to 2, it means that every set of k lines in the plane, no two of which are parallel, they meet in a common point. And if you want to prove the property of k plus 1, it means that you want to prove for every set of k plus 1 lines in the plane, no two of which are parallel, um, they meet in a common point. Good. Can we prove it? Yes. Actually, if we assume if we have this wrong assumption about the property being true for every k that is greater than or equal to 2, without checking the case for k equal to 3. So actually, if k is equal to 3, then p of k is false. It's not true. But if we don't check this, if we just assume it for every k greater than or equal to 2, then this wrong assumption leads us to the wrong conclusion that the property is also true for k plus 1. So in the case of a set of k plus 1 distinct lines in the plane, two of which are parallel, by the inductive hypothesis, if we consider the first k of these lines, they must meet in a common point, P1. If we consider the last k lines, then they must meet in a common point, P2. If P1 and P2 are different points, then all the lines containing both of them must be the same line, since 2 points determine one single line. Okay, so the idea is somehow if you have these n lines, k plus 1 lines, if I consider, let's say, the first k lines, if they meet in a certain single point, call it P1. And if I consider another subset of lines, yeah, then if they meet in a certain common point P2, then P1 and P2, they must be the same, okay? In my case, all these lines pass by a certain point. Otherwise, it won't be actually possible, okay? So that I can't draw, I can't make for you a drawing where we have k different lines that meet in a single point and k other different lines that meet in a second point. So once you draw k lines that meet in a certain p1 point, common point, and uh, you take a k minus 1 of these lines and you add one line to them that passes through another point, then these 2 points must be the same. Um, so if P1 and P2 are different, then all the lines will collapse. And this contradicts the assumption that the lines are distinct. So if the lines are distinct, then P1 and P2 must be the same. Okay? Uh, and since they lies on all the k plus 1 distinct lines. And then this means that the property must hold for k plus 1. Okay? So, assuming that the property is true for every k, we found out that the property is necessarily true for k plus 1. But is it really a sound proof? The problem is that we haven't checked these other cases. So actually, the implication is true just because the premise or the inductive hypothesis is false at the first place. It's false for 3, and it would be false for any k greater than or equal to 3. It's only true for the base case, which is 2. So as you notice, the choice of the base case is tricky sometimes. Um, sometimes your property is false at the beginning and then it's true afterwards. Sometimes it's true only at the beginning, but it's not true afterwards. So as we did with the example of 2 to the power n and factorial of n. So the choice of the base case is crucial. And sometimes you need also strong induction to have stronger assumptions over all the values less than a certain rank k. So to sum it up, a proof by induction requires to determine the basis step and to prove it. Usually this is straightforward. Then to write the words inductive step and to make your assumption about the property at the step number k, and to make it for an arbitrary fixed integer k that is greater than or equal to b, greater than or equal to your base step, to state what needs to be proved for k plus 1 so that you can play with your inductive hypothesis or simply use it correctly to prove the property for k plus 1. Okay, and the idea is to make the implication that p of k implies p of k plus 1 true for an arbitrary k. If this is done, then you can assume finally by induction that p of n is true for all integers n that are greater than or equal to your base step. Okay, that's it. I will have your questions in the class, in the next classes, and eventually I will make another video for strong induction. Thank you for listening, and see you soon.